This is Module 2, Lesson 3, and we're going to be discussing measures of variation. Let's think about it for a minute. Is an average, like the mean, the median, or the mode, enough to describe a data set? My gut says no. Let's consider an example. A shoe store owner knows that the average size of a man's shoe is a size 10. But if she only stocked size 10 shoes, I don't think she'd be in business very long. Because if a customer comes in who needs a size 12 and she doesn't have a size 12, she can't make a sale. Or if a customer comes in and needs a size 9 shoe and she doesn't have a size 9 shoe, again, she can't make a sale. So it doesn't make sense for her to only order size 10 shoes. So what else do we need to know? We need to know how the data is dispersed. How do the men's shoe sizes vary for the population or for her customer base? Do they cluster around the center so that maybe she could get by with ordering like size 9 to 11? Or are they spread out more evenly so that she needs to carry, 7, 8, 9, 10, 11, 12, and so forth? That's where we get into the measures of variation from a statistical point of view. How much does the data vary, or how much are they spread out? There are 3 measures of variation we're going to consider: the range, the variance, and the standard deviation. Let's talk about the range first. You probably have heard of the range. The range is the simplest of the 3 measures of variation. It's calculated very easily by subtracting the minimum from the maximum. Now, it's not the best measure to use because you're only considering the high and the low. So it just gives us kind of a place to begin, because if the range is reasonably small, that lets us know that our data is kind of clustered together. If it's a larger value, that lets us know that our data is more spread out. Second is the measure of variance. Variance is a lot more useful than the range, because the formula, which is very convoluted and we'll look at in just a minute, looks at how each individual data value differs or varies from the mean. So we're using all the data values instead of simply the low and the high, and we're comparing it to our measure of center, the mean. The variance is what we consider an unbiased estimator within statistics. Now, what that means is that the variance for the sample tends to target, almost like hitting the bullseye, for the variance of the population. So the variance for a sample tends to be right on target for the variance of the population, without systematically overestimating or underestimating. That's what makes it unbiased. So it's a good one to use when you're trying to look at the values for your population as opposed to the sample. There is one major disadvantage to using the variance, however. Within the formula and the calculations that are performed, you have to do some squaring. And so ultimately, your units of measure become squared. And at least in my mind, it would be difficult to interpret a square shoe size, or square dollars, or square years. Those are not things that we traditionally deal with. And so it makes the interpretation of the variance very difficult, if not impossible. I am going to show you the formula, but again, please do not get caught up in the formula and the symbols, because we are going to use the technology to help us perform these calculations. If you want a detailed explanation of how this formula is developed, there is a Word document under Module 2, the extra notes, entitled Descriptive Statistics that actually walks you through the development of all the various formulas. The one thing I do need you to know is that the symbol for population variance is this little O with an exponent of 2. The 2 indicates that we've squared it. The little O looking symbol is the Greek letter sigma, so we read this sigma squared. For the sample variance, remember we use English letters for the sample, and we use the letter S. So S with an exponent of 2 represents your sample variance. And again, you may want to be familiar with those two symbols because, again, they will show up in research articles, or you'll need to use them whenever you are conducting research. Third is the standard deviation. The standard deviation is simply the square root of the variance. So we take that variance and take the square root, and the benefit of that is that that returns your units of measure to the original data. So now we can talk about just straight shoe size or dollars or years. And again, that makes it easy for us to interpret because we're used to dealing with those things. The standard deviation, along with the mean, is one of the most important measures for a data set. Again, because it uses all of the data values, and it also is used in other statistical calculations, as we'll see a little bit later. So the standard deviation provides us a numerical measurement of how we might expect a typical member of the data set to differ from the mean. The greater the standard deviation, the more the data is spread out or varies. The standard deviation allows us to interpret the differences from the mean with a sense of a scale. We get to make a sense of whether the difference is large or small in a more systematic way. One thing I want to point out to you is that standard deviation will never, ever be a negative value. Because if you'll recall from your algebra days, the square root of a negative value is imaginary. Well, within statistics, we're dealing with real data, real numbers, and so we would never have a negative value for the standard deviation. So how do we use this? We primarily would focus on either the variance or the standard deviation when we're calculating measures of variance. Again, the range is okay, but it's not as useful as these two. So how do we use it? Why do we need to know these things? It's a lot more useful than the range simply because it considers all of the data values. It can help us to determine the spread of the data. If the variance or standard deviation is large, that tells us the data is more dispersed. And if we're trying to compare two or more data sets, we can look at which one has the higher standard deviation or the higher variance, and that tells us that that particular data set is more variable or more spread out. We can also use it to determine the consistency of a variable. For example, in manufacturing of fittings, things like nuts and bolts, the variation in the diameters of the nuts and bolts must be small and consistent, or the parts won't fit together. Okay, so examples. And we'll look at those in another video, again, all at once to see how to calculate measures of center, measures of variation, and also measures of position using the different technologies. I want us to get through all of the discussion first.